If all particles of matter at room temperature have the same average kinetic energy, then why are some gases and some liquids and some solids? The answer lies in the attractive forces between particles. We call those intermolecular forces. Let's get started. First, let's differentiate between what we call intramolecular forces and intermolecular forces. Like the prefix suggests, intramolecular forces have to do with forces that are inside the molecule or holding the formula unit together. Things like covalent bonds or ionic bonds or even metallic bonds. Intermolecular forces are attractive forces that occur between one molecule and another, or one molecule and another particle. So we're going to talk about four types of intermolecular forces. The first type is called London Dispersion Force. The second, Dipole Attraction. The third is known as hydrogen bonding. And the fourth would be called Ion Dipole Attraction. So how does the strength of intermolecular forces compare to that of intramolecular forces? Intermolecular forces aren't nearly as strong as intramolecular forces. And that's a good thing too. Can you imagine trying to dive into a pool and not being able to break the surface of the water? That's what would happen if intermolecular forces were just as strong as intramolecular forces. So in order of weakest to strongest, the London dispersion forces are the weakest, followed by dipole attraction. Then you have hydrogen bonding near the top, with ion-dipole interactions being among the strongest. Let's talk about London dispersion forces first. The London in London dispersion forces comes from Fritz London, the scientist who first described them. As we said previously, London dispersion forces are among the weakest of the intermolecular forces. London dispersion forces occur between nonpolar molecules or neutral atoms. Here's what happens with London dispersion forces. Let's say we have two neutral atoms or even two molecules that are nonpolar. Nonpolar meaning that the electron density around that atom or molecule is very balanced. There's no greater density on one side of the molecule or atom than another. For example, let's say that we have two helium atoms. Normally those are very inert. They're among the noble gases. But what happens when one helium atom comes in close proximity to another? Well, then the nucleus of one helium atom is attracted to the electrons of the other. At the same time, those electrons are slightly repelled from the electrons of the other helium atom, and so then you have a slight temporary imbalance that occurs, where the electron density around that nucleus is sloshed over to one side for each of those helium atoms. This causes a slight bit of negativity on one side and a slight bit of positivity on the other. Just to be clear though, this is only temporary. Remember, as soon as those helium atoms move apart from each other, they'll go back to being ordinary inert atoms with no electron imbalance, no negative end and no positive end. We call this a temporary dipole, or sometimes an instantaneous dipole. So now that very small bit of negativity on one helium atom is attracted to the very small bit of positivity on the other one. And voila, you have a dispersion force. These are indeed the weakest of intermolecular forces, but if you're a nonpolar molecule or a neutral atom, this is really all you have to pull each other together. So nonpolar molecules can work in the same way. Normally they have nice balanced electron density around the molecule, until they come into close proximity to another molecule. Then they have that slight imbalance, a temporary dipole situation. Dipole meaning that there are two poles, right? A positive end and a negative end. So even if you're a nonpolar molecule, it's still possible to have some attractive force to another molecule through London dispersion forces. And if you're a larger nonpolar molecule, then you can have more opportunities for London dispersion forces because of the fact that you have more electrons at your disposal. So London dispersion forces are proportional to the mass of the molecule, really. The larger nonpolar molecules have greater opportunities for dispersion forces, and the smaller ones have less opportunity. That's why normally we see that small nonpolar molecules occur in gaseous form, while the larger ones can have the opportunity to form liquids at room temperature. Just to give you some idea, here's a graph showing the various boiling points of hydrocarbons. Hydrocarbons are carbon and hydrogen molecules that are definitely nonpolar, and you can see that as the mass of these molecules increases, so too does the boiling point. Now these boiling points, by the way, are in Kelvin. If we do the math, we can see that methane has a boiling point of around negative 161 degrees Celsius. Very, very low, right? That's why normally methane is seen in gaseous form, in room temperature. On the other end of the graph, though, we see octane, C8H18. Octane is a much larger nonpolar molecule, so therefore it has more opportunity for London dispersion forces. And octane actually has a boiling point greater than that of water. Let's recap for a second. Nonpolar molecules and inert atoms can only have dispersion forces as their intermolecular forces. Remember that in this situation, the nonpolar molecule or the inert atom forms a temporary dipole or instantaneous dipole. It doesn't last forever, it's only while that dispersion force is in effect. That's why a lot of nonpolar substances are so easy to boil. It's fairly easy to overcome those London dispersion forces. But that changes just a little bit when we move up to our next level, that of the dipole-dipole attraction. Now, if we have a molecule like hydrogen chloride, we know that the chlorine is going to be more electronegative than the hydrogen is. So that electron density will sort of slosh to one end, toward the chlorine. Remember the analogy of the trampoline we talked about? Let's say that we have a waterproof trampoline, and on one side you have a person of very heavy weight, and on the other side a person of very light weight. Next, let's say that I poured a big container of water on that waterproof trampoline. Where would the water pool? It would pool around the person of heavier weight, wouldn't it? We can use that as an analogy for electronegativity. The heavier atoms are the ones that have greater electronegativity, and therefore the electron density will pool around them more so. So chlorine in this case has greater amounts of electron density and therefore is the slightly negative end of this molecule, while hydrogen is the slightly positive end. Again, we describe this as polarity. Remember that when we say that something is polar, we mean that there are two poles on that molecule, a more positive end of that molecule and a more negative end, where the electron density is the strongest. And more specifically, we say that this molecule has a dipole, two poles, a slightly positive one and a slightly negative one. Now this is different from the situation we had with those nonpolar molecules and inert atoms that were forming dispersion forces, because these dipoles are permanent. These molecules always have two poles, always one side that's positive and always one side that's negative. In fact, sometimes you'll see this symbol, an arrow with a plus sign on one end, to indicate the presence of what we call a dipole moment. You could think of it as the arrow pointing to the direction in which that electron density flows best. So, whenever you have one of these permanent dipole molecules close to another permanent dipole molecule, the slightly positive end of one is attracted to the slightly negative end of the other. We call this dipole-dipole attraction. We can see it in this example of two hydrogen chloride molecules being close together. The slightly positive hydrogen on one molecule is attracted to the slightly negative chloride on the other molecule. Incidentally, hydrogen chloride gas is what we use to make hydrochloric acid. When you have more of these dipole molecules together, they can form all sorts of attractions. And the more attractions that they have, the more strongly they stay together. Typically speaking then, a substance that has dipole-dipole attraction going on has a higher boiling point than that of one that just has dispersion forces. The cool thing about these intermolecular forces is that they can be compounded. That is to say that a substance that has dipole-dipole attraction can also have dispersion forces going on as well. It's like a twofer. It's just the nonpolar molecules that only have dispersion forces. The third type of intermolecular force is called hydrogen bonding. This is a specific type of dipole-dipole bond, but as you can guess, it involves hydrogen. In this case, hydrogen is bound to a very electronegative element, nitrogen, oxygen, or fluorine in particular. Whenever hydrogen is bound to one of these highly electronegative elements, the electron pooling is really intense. The density really flows around that electronegative element more so than hydrogen. So the slightly positive effect and slightly negative effect is a little more profound. That being the case, the positive hydrogen now finds itself attracted to an electron pair on an adjacent molecule, that electron pair belonging to a nitrogen, oxygen, or fluorine. We find hydrogen bonding in substances like ammonia. The nitrogen in ammonia is much more electronegative than hydrogen is, and so that electron density flows more around the nitrogen. The now positive hydrogen is attracted to an electron pair on a nitrogen on another molecule. Water is great at hydrogen bonding. As a matter of fact, each water molecule has the capacity for 4 hydrogen bonds. You have 2 hydrogens on each molecule and 2 electron pairs on the oxygen of each molecule. Because of this, the water can form tetrahedral hydrogen bonding. By the way, hydrogen bonding is one of the reasons why snowflakes have their hexagonal shape. Hydrogen bonding is also seen in DNA. It's what allows for that double helix shape. Each thymine-adenine combination has 2 hydrogen bonds, and each guanine-cytosine combination has 3 hydrogen bonds. So if it weren't for that hydrogen bonding, no double helix. Just like substances with dipole-dipole attraction, substances that have hydrogen bonding also have the benefit of dipole-dipole attraction and dispersion forces. The last type of intermolecular force is that of the ion-dipole force. In an ion-dipole force situation, you have ions from an ionic compound that are attracted to the dipole of a polar molecule. A great example of this is sodium ions and chloride ions when they are dissolved in water. You can see how the molecules of water will arrange themselves around that sodium ion or that chloride ion. Not only that, but those water molecules will arrange themselves in such a way so that their negative oxygen ends are pointing towards the positive sodium ions, and the positive hydrogen ends of the water molecules will point themselves toward the negative chloride ion. That attractive force is very strong, and this allows water to be able to dissolve a great many substances. This is extremely important because virtually all biochemical reactions take place in water. That's why water is known as the universal solvent. We'll talk more about this feature when we get to our study of solutions and solvation. When you stop to really consider it, intermolecular forces are an amazing feat of engineering and design, considering how it allows water to be that powerful solvent needed for those biochemical reactions, the hydrogen bonding that allows for the double helix shape in DNA, not to mention to give the shape of proteins that are absolutely necessary for metabolic processes, sometimes as specific as, say, a key would be to a lock. That's remarkable. Hydrogen bonds give water its high surface tension. Those intermolecular forces provide water with its adhesive properties that allow it to travel into the roots and into the stems of plants and trees. Not to mention how critical they are for moving components through the soil to get to those trees in the first place. We can even see the incredible balance of the intermolecular forces in water's viscosity. Viscosity is the resistance of a substance to flow. Water has just the right amount. If it had too high a viscosity or too low viscosity, water wouldn't be able to transport oxygen and nutrients in sufficient quantities to cells in order to support life. Like I said before, that's an amazing amount of engineering and design going into intermolecular forces. And it makes sense because, after all, Paul tells us in Colossians 1, "In Him all things are held together." That's all we're doing for this video. Today we talked about intermolecular forces. We started with the weakest, the dispersion forces, and worked our way up through dipole-dipole attractions, hydrogen bonding, and ion-dipole forces. This information will lead into our next video talking about solids and liquids and how intermolecular forces help us to have a solid or a liquid. So I hope this has been helpful to you, and until next time, God bless.